Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad, India. Today we are going to study what is rubbing velocity and introduction to acceleration analysis. This topic comes under the subject of kinematics of machines and module number 2. So what is rubbing velocity? It's very simple to understand. Whenever two links are rotating each other and those two links having different angular velocity, and the angular velocities, difference of angular velocities or algebraic sum of angular velocities multiplied by the radial distance of the pin joint or pin, then it is known as rubbing velocity. In this figure, there are two links, that is OA and OB. The OA is rotating with angular velocity omega 1 in a clockwise direction, and OB is rotating with the angular velocity of omega 2 in counterclockwise direction. And what is the rubbing velocity at the pin O? Let me read. The links in a mechanism are mostly connected by means of a pin joints. The rubbing velocity is defined as the algebraic sum between the angular velocities of the two links which are connected by pin joints multiplied by the radius of the pin. Here, if you understand, the pin may be small, but that radius may be having. So, the angular velocities, why it is algebraic sum? If the both pins are rotating in opposite direction, then it may come one notation. We have to either add or adding or subtracting based on the rotation of the pins and based on the rotation of the links, not pins. Now, considering here, there are two links are there. The two links, we are considering the two links. The two links are OA and OB and connected by a pin joint O as shown in this figure. Now, if you see here, this link OA having angular velocity, that is omega 1, and it is rotating with respect to pin, that is O, and omega 2 is the angular velocity of the link OB or the angular velocity of the point B with respect to O. That point B with respect to O, that is the absolute velocity, and angular velocity is absolute angular velocity omega B. That omega B is denoted with omega 2 here, denoted by omega 2. And what is radius? The radius R is the radius of the pin. So according to the definition, the rubbing velocity at the pin point, at the pin joint O, that equal to omega 1 minus omega 2 times radius of the pin R, when provided if the links move in the same direction. If the links move in the same direction means the links may be both are OA and OB are rotating in the same direction, either clockwise or counterclockwise. Then the formula for rubbing velocity at the pin joint O equal to omega 1 minus and omega 2 difference, omega 1 minus omega 2 multiplied by R, radius of the pin. Suppose in this figure, the links are rotating in opposite direction. Then what is rubbing velocity? The rubbing velocity will be added together, that is omega 1 plus omega 2 times R, if the links are moved in opposite direction. So that is a rubbing velocity formula. And very important here, we are going to consider another case study. If the pin connects one sliding bar and the turning member, the angular velocity of the sliding member, what is the angular velocity of the sliding member? Is 0. In that case, in such cases, what will happen? What is the formula? The rubbing velocity at the pin joint equal to omega times r. So this type of case is observed in the case of a slider crank mechanism, where the slider is connected to connecting rod. This is a slider crank mechanism, link 1, 2, 3, 4. Here the link 3 is connected to link 4 slider. So what is the rubbing velocity link 3 and 4? The rubbing velocity at 3, what is the, there are two links are there, link 3 and 4. The angular velocity of the slider is 0 because the slider is moving horizontally. It is not in rotary motion. It is not some angular. It is not under rotation. It is under reciprocation. When it is under reciprocation, what is the angular velocity for that link? Is 0. Now substitute in this formulas, any one of the formula, make it omega 2 is 0. Then what will happen? Then it becomes omega 1 times r. What is it omega 1 here? The link of which is in under rotation. That is omega times r. Omega is angular velocity of the turning member, and where r equal to radius of the pin. Alright, this is the way one has to find out the rubbing velocity at a pin joint. Okay, now the rubbing velocity can be taking place where we can observe when the two links are rotating in opposite direction. If we consider the 4-bar mechanism or 5-bar mechanism or any other mechanisms, you can observe this type of cases where both are rotating in opposite direction. In the case of 4-bar mechanism, you can understand what is the rotation of the link 3 and 4. Based on the direction of the rotation, okay, we can understand, we will use this rubbing velocity formula is applied according to the rotation between two links. As I mentioned here, if the two links are rotating in the same direction, then the formula of rubbing velocity is omega 1 minus omega 2 times radius of the pin. If two links are rotating, the two links are link 1 and link 2 are in both, suppose link 2 and link 3 are rotating in opposite direction, then what? Then what is the formula? The formula for rubbing velocity is omega 2 plus omega 3 times radius of the pin joint here, 2 and 3 joint here. And if we consider in this, if we consider the rubbing velocity at link 1 and 2, what is the rubbing velocity? That is omega 2 times radius of the pin at 1 and 2 joint. What is omega 2? Angular velocity of the link 2. What about omega 1? The omega 1 is the angular velocity of the fixed link, that equal to 0 for fixed link, for this case 0. Similarly, if we want to study the rubbing velocity between link 1 and 4, what is the rubbing velocity formula? Anybody can say? That is omega 4 times radius of the pin, where? At 1 and 4 joint. This is the one. Thus, we will study the rubbing velocity of various pin joints of various links. Okay, next. What is the acceleration diagram for a link? What is the acceleration diagram? Okay, the acceleration for this is You understand, very important it is. There are two types of accelerations. One is radial or centripetal acceleration, and second one is tangential acceleration. So we are considering in this figure, there are different points. There are 2 points on the link. Yes, we have studied in the case of velocity, this is a tangential acceleration and radial acceleration acts along the link. Radial acceleration acts along the link. So I want to maximize this picture so that it will be visible. So you can see more clarity here. In this acceleration, consider there are 2 points are there in this diagram. Link. This is the link. On the link we are considering 2 points A and B. We are going to find out how to draw the acceleration diagram for this link. It is very, very important. If you understand this concept, we can draw acceleration diagram of various mechanisms of various links. Let me read step by step points so that, and I will explain here so that you will understand better. We are considering 2 points A and B on a rigid link, which is shown in figure. Okay. Next, let the point B, this VBA is the tangential, that is called tangential component acceleration. And when it is acting ARBA, that is radially downwards. So let the point B moves with respect to A with an angular velocity of omega radians per second and acceleration alpha radians per second square of the link AB. Because to draw the acceleration, yes, let me introduce little bit. Acceleration equal to dv by dt, where v is the velocity, rate of change of velocity is known as acceleration. Rate of change of displacement is known as velocity. If we want to draw the acceleration diagram, or if you want to observe the acceleration values of various links, we need the velocity values. So if you want to draw any acceleration diagram without velocity diagram or without velocity values of particular links, the acceleration diagram can't be drawn. That is very important. If acceleration diagram is to be drawn, that means velocity diagram to be drawn already. It should be. Otherwise, we cannot draw acceleration diagram. So, for every acceleration diagram, we should draw before that velocity diagram should be drawn. Now, why this acceleration depends on the velocity. So unless and until velocity values are not calculated, acceleration diagrams can't be drawn. That is very, very important concept. Now if we want to draw suppose we know velocity values, then only we can begin to draw the acceleration diagram. Now acceleration of a particle whose velocity changes both in magnitude and direction at any instant of time has the following 2 components. Okay, again, acceleration of a particle whose velocity changes in both in magnitude and direction at any instant has the following 2 components. What are the components are? Number 1, the centripetal or radial component, and which is the radial or centripetal component, which is perpendicular to the velocity of the particle at the given instant. this radial or centripetal is perpendicular to the velocity. That means it is in line with the link. That is perpendicular to velocity component. That means it is in line with the link. Next type is the second component is a tangential component. This tangential component is parallel to the velocity of the particle at the given instant. These two rules are very, very important. For every particle having two components, two acceleration components, one centripetal or radial component, second one is a tangential component. The sum of these two gives the value of a total acceleration of a particular link. So, what is the direction of these two? Say radial component direction is parallel to the link or perpendicular to the velocity component. Okay, and the tangential component direction is tangential component perpendicular to the link and parallel to the velocity component. Okay, parallel to the velocity of the particle. So if you are taking the reference of velocity diagram and drawing the diagram, then we consider that rules related to velocity component. That means if you are taking the reference of velocity diagram and drawing acceleration diagram, then what to be done? For a radial component, it is perpendicular to the velocity component. And for tangential component, it is parallel to the velocity diagram component. And if you are considering the reference of configuration diagram, it is opposite. If you are taking the reference of configuration diagram and drawing acceleration diagram, then what is happen? What are the rules are? For radial component of acceleration, it is parallel to the link. For tangential component, it is perpendicular to the link of a configuration diagram. You pause again and again, you hear this what I am saying rules, no confusion at all. But based on what reference you are going to draw, you are taking the reference of configuration diagram or you are taking the reference of velocity diagram. Which diagram you are going to consider for drawing acceleration diagram? That is important. Based on that, you have to follow the rules. Then we can draw. Now, coming to the subject. Thus, for a link AB, we are considering to this figure, link AB, the velocity of point B with respect to A, that is VBA, is perpendicular to the link AB is shown, VBA. Since the point B moves with respect to A with an angular velocity omega radians per second, therefore the centripetal or radial component of the acceleration B with respect to A, that is ARBA, that is radial component, that is omega square times length of AB. Now here, that is omega square times AB, that omega times AB, that equal to, what is AB equal to? Again, omega equal to VBA by AB whole square. That AB get cancelled, then it becomes V square BA by AB. So this is the formula for radial component. The radial component is V square by R. That's it, simple. That V square by R. What is the V velocity of the link, particular link, by R? R is means that length of the link here. That is V square by R. Next, tangential component of the radial component of acceleration. How it acts? Acts perpendicular to the velocity, or in other words, yes, it acts parallel to the link AB. Very, very, very important. This parallel to the link AB related to configuration diagram. Perpendicular to the velocity, perpendicular to the velocity VAB, that is related to where? Velocity diagram. Okay. Next. Now here, we know that now so far we covered, what we have covered is only for radial component of acceleration to draw the which diagram? Acceleration diagram. Now we are going to study what is tangential component of acceleration. This tangential component of acceleration, we know the formula Vt equal to r times alpha. What is that alpha? Okay, r times angular acceleration alpha. Angular acceleration times radius of the link or length of the link. That is tangential component of B with respect to A equal to AT equal to alpha times length of the link AB. That is alpha times AB. These are the formulae. How it acts? The tangential component of acceleration acts parallel to the velocity link VBA, or in other words, perpendicular to the link AB. This perpendicular to link AB related to configuration diagram. Parallel to the velocity VBA, it is related to where? Velocity diagram. So these are the principles to understand before going to draw. This diagram is the acceleration diagram. Okay. Now, here, in order to draw the acceleration diagram for link AB, from any point B dash, draw a vector, that is B dash X parallel to link AB or parallel to link BA. That is the radial component of acceleration. B with respect to A, that is the radial component. That is ARBA. We have drawn parallel to link BA. We have drawn parallel. Next, there is another component, is the tangential component. Now, the tangential component, draw vector XA dash, that is perpendicular to BA, to represent the tangential component of acceleration. Okay, that is tangential component of acceleration, that is of B with respect to A, that is ATBA. Now join B dash to A dash. What is the B dash to A dash? That is the vector B dash A dash, known as the acceleration image of the link AB. So, the acceleration of the link AB equal to ARBA plus ATBA. This acceleration, that is called total acceleration. The total acceleration equal to of link AB equal to radial component of acceleration plus a tangential component of acceleration. For each link, if you want to draw the acceleration diagram, we have to draw radial component of acceleration and a tangential component of acceleration. Join these two, then it comes the total acceleration. Now, one more important. The radial component of acceleration and the tangential component of accelerations are normal to each other, perpendicular to each other. If it is radial, yes, radial, and perpendicular, it is tangential. Joining these two, that is the total acceleration, that is the vector presentation, that is the acceleration diagram. That is, this acceleration diagram is for the link AB. We have drawn for this link AB. This is the acceleration diagram. Now, the total acceleration of B with respect to A, or total acceleration of B with respect to A, B, A, it is the vector sum of radial component and tangential component of acceleration. Radial component and tangential component of accelerations. What is the vector sum? Vector sum of. Okay, very important concept of how to draw the acceleration diagram of a link AB. So here, if we consider any mechanism like simple slider crank mechanism, there are how many turning pairs are there? There is one sliding pair and remaining all are turning pairs. So this is slider crank mechanism. Okay. In the slider crank mechanism, fixed link 1, 2, 3, 4. We have to draw link 2. Link 1 is fixed. There is no neither tangential nor radial component for fixed link 1. But if you consider link 2, then link 2 is having both radial component and tangential component. And link 3 is also having both radial and tangential. Whereas link 4 slider becomes one of the acceleration becomes absent because it is not under rotary motion. Okay, it is under purely reciprocatory motion. So for this link, you may be having a tangential component of acceleration. There is no radial component of acceleration for the link 4, that is the slider here. So radial component of acceleration equal to 0. Then the total acceleration equal to, in this case, what is the total acceleration equal to? Radial component of slider plus tangential component of slider. This radial component of slider is 0. Then the total acceleration of slider is tangential acceleration. So thus we will find out particular link, how it is under rotation, whether it is in rotation or combination of rotation and reciprocation. Based on that, we will take the values and draw acceleration diagram. Now, acceleration of a point on a link. Again, we are considering what is the acceleration of a point on a link. So, it is a point. There are 2 points are there. Consider, let us begin, let us read. So, we'll understand better, step by step, we will draw. We are considering here, consider 2 points, A and B, on the result link AB. Let the acceleration of point A is AA is known in magnitude and direction. In magnitude and direction we know. And direction of path point of B is given. Here point A, both magnitude and direction both known. But point B, we know only direction. We don't know magnitude. As we have studied in the previous session, that is introduction to velocity and acceleration analysis, we considered the same case for doing velocity analysis. That is velocity of a point on a link. Under that headline we studied. Now, but here we considered acceleration of a point on a link. Now, the acceleration of the point B is determined in magnitude and direction by drawing the acceleration diagram as discussed below. Now, first point, what is the first point? From any point O, draw vector OA dash that is parallel to the direction of absolute acceleration, that is AA, to some suitable scale as shown in this. We are drawn, okay, point any die, that is known scale we have drawn. What is the second step? That is O dash, A dash. We have given. In this acceleration diagram, we will give O dash and A dash. As an engineering drawing, no, top view and front view notations are different. Like that, in acceleration diagram, total acceleration, there is no notations, there is no dashes. But here, each acceleration component is the sum of radial and tangential. For radial and tangential components, we will follow. Alright. Next. Now, next step is, we know that the acceleration of B with respect to A, that is ABA, has the following two components. What are the components? Are radial component and tangential component. The radial component, okay, that is denoted by AR BA dash, and it is AT BA, that is tangential component. But these two are mutually perpendicular to each other. Now, next step, draw a vector A dash X to the link AB, because radial component is parallel to the link AB, okay, passes through. Now, what is that vector A dash X is? We know VB square by R, that is V square BA by AB. From that you draw where BA is the velocity of B with respect to A. We should know already before velocity values of each link, velocity components, then only we can draw, because we need velocity values of each link. Now that is V square BA by AB, that is VB is velocity of B with respect to A. Now after that, what is the next point? We have drawn up to here. The second step, next step is, from point X, draw a vector XB dash. What is that XB dash is? Tangential component. Because the tangential component of B with respect to A is perpendicular, we have drawn, that is ATBA is perpendicular and to the radial component, but we don't know what is magnitude, okay. And through O dash, draw a line, through O dash, draw a line parallel to the path of B. Draw a line parallel to the path of B. So this is the line parallel to the path of B to represent the absolute acceleration of B, that is AB. The vector XB dash, the vector XB dash and OB dash intersect at the point B dash. Okay. Now the values of AB and ATBA may be measured to the scale. If you measure O dash to B dash, that is acceleration, O dash to B dash, that is nothing but acceleration of the point B with respect to O. Measure to the scale O dash B dash vector and convert to the scale. Thus that value gives the acceleration of point B. Now if you measure the XB dash vector value gives the value of which value? Tangential component of B with respect to A. Okay. We know here in this problem, we know only O dash A dash, both magnitude and direction, and we know the magnitude and direction of ARBA, but we don't know ATBA, we don't know the value of AB. So how we have calculated the unknown values of, that is tangential of link BA, that is tangential component of acceleration, and total acceleration of point B on the link A, on the result link. Thus we can calculate. Let us begin. Once again, what we have drawn. So here, first step, we know the magnitude and direction of AA. With respect to O dash to A dash, we have drawn. Yes, O dash to A dash. And we know the radial component of acceleration of AB. It comes under V square by AB, VAB. From that, what came out? Radial component of acceleration, AR, AB we know. That with known magnitude and direction A dash X. We don't know the tangential component, but according to based on the concepts of acceleration diagram, It is perpendicular to the radial component of acceleration that we have drawn. We don't know where it will intersect. We have drawn perpendicular to that. Then what is that? Next, we have to do it. What we have to do it? With the known, next, what is next? Total acceleration. The total acceleration comes when we from O dash to that line you draw parallel to that. That is the total acceleration. Very important here. From point x dash, draw vector xp dash perpendicular to AB. Yes, xp dash perpendicular to AB. Perpendicular to link AB, that is parallel to VBA. Next is perpendicular to radial component, and through O dash, draw a line parallel to the path B. What is the parallel to the path B? This is the tangential path B they were given. Tangential path B. The tangential path B, that means normal to perpendicular to the link AB, that is also, but you have to start with O. If you draw that, then what will happen? It will intersect the link, the tangential component. This OB dash is the total acceleration of two components. What are they? Total acceleration of radial component and tangential component. That is the total acceleration of OB dash. Now one more step. The one more step is that this is ARBA, it is ATBA. The BA link total acceleration is, ABA. ABA is the total acceleration of B with respect to A, that equal to algebraic sum of or ARBA, sum of ARBA and ATBA. This is the line. Thus, we can draw, this is the velocity diagram of link AB based on the figure is given below. So, these are the different of the joining points which are measured here, mentioned. How to do it, velocity of, how to draw the acceleration diagram of the link. Okay. This is the fifth point. That fifth point is mentioned already here, drawn. Very important concepts, how to draw the acceleration diagram. Okay. Now, that is, so far we covered what is velocity diagram and how to draw the acceleration diagram, what is rubbing velocity of various links. Okay, next one. Now we are going to solve one problem that purely, I think so, it is related to acceleration, how to draw the acceleration diagram. The crank of a slide crank mechanism rotates with an angular velocity in clockwise direction at constant speed of, not angular velocity, at constant speed of 300 revolutions per minute. The crank length is 150 millimeter and the connecting rod AB, that equal to 600 millimeter. Determine the linear velocity and acceleration of the midpoint of the connecting rod. Midpoint of the connecting rod. This is a connecting rod AB. Midpoint of connecting rod is D. And angular velocity and angular acceleration of the connecting rod. Again, angular velocity of connecting rod AB and angular acceleration of connecting rod at a crank angle 45 degree from the inner dead center position. So there are two objectives are to be found in this problem. So based on the data, we have to calculate whatever we can calculate, we can analytically to the extent. Based on this data, we can calculate VBO, that is velocity of B with respect to O, that is VB equal to omega BO times OB. Omega BO, that is 2 pi n by 60, that is the crank. 2 pi times n, 300 by 60, that is 31.42 radians per second. Okay. And what is the length of OB? The length of crank length is 150 millimeters. That is converted to meters, that is 0.15 meters. That is 31.42 times 0.15, that is 4.713 meter per second. That is omega BO. Yes, omega BO equal to 4.713 meter per second. So, to draw the velocity polygon, first step, draw vector OB perpendicular to some suitable scale. We know OB, velocity BO we know. Yes, before slide we know, that is VBO equal to 4.713 meter per second. You consider 1 meter per second equal to 1 centimeter to draw the vector diagram. Some suitable scale, choice is yours. You can consider 0.5 meter per second equal to 1 centimeter, also okay. But if 1 meter per second equal to 1 centimeter, the vector OB equal to how many centimeters? 4 point converted into 0.713 something. That is the vector length. Now, to draw the velocity polygon, we are going to draw first velocity diagram. It is a space diagram. Another name of space diagram is configuration diagram. This is very important diagram. You have to redraw in your answer script. Configuration diagram must be drawn from the question paper to your answer script. Exactly, you have to take reduction scale. That is 150 millimeter is there. You again reduce the scale. That means it is 15 centimeters. And the length 45. Reduce the scale by 2. It becomes 75 millimeter. And reduce the AB also proportionately. And draw the configuration diagram. Redraw the configuration diagram into your answer script. Then from the configuration diagram, with the help of set squares, how to draw? You have to use either mini drafter or what? Set squares. There we need 2 set squares are required. In the next class, I am going to show you literally how to draw acceleration diagram, velocity diagram and acceleration diagram from the configuration diagram, and how to draw the configuration diagram from the question paper. Alright. That is here. The first step, draw vector OB perpendicular to the link BO. We are drawing vector velocity polygon or velocity diagram. For that rules. The rules are, draw vector OB perpendicular to BO to some suitable scale. To represent the velocity of B with respect to O, or simply velocity of B, that is VBO. That is how much? Vector OB equal to 4.713 meters per second. Okay. Next step. That is the first step we have to draw. We have drawn. That is velocity of B with respect to O. Second step. What is the second step? From point B, draw vector BA perpendicular to small letters. BA small letters indicates into the velocity diagram. Capital letters relates to configuration diagram. From point B, draw vector BA perpendicular to capital letters BA, perpendicular to configuration diagram link. That is velocity of A with respect to B. That is VAB. And from point O, draw vector OA parallel to the motion of A. Here the motion is parallel with respect to fixed link. No, A with respect to O. But you draw two things. One is perpendicular to AB line. Another one is parallel to with respect to a line. The vector BA intersects OA at A. Let us see. This is VBA line. The VBA line, that is velocity AB or BA line, is perpendicular to the configuration diagram line AB. What is that we have drawn? We don't know. We know the direction. We don't know the magnitude. Okay, but and the length also we know. What is the length? We don't know length also VAB, but you have to draw. And next one is that velocity of A with respect to fixed length. Dotted line it is a parallel line because of translatory motion, linear. Draw a line, that is the VA. Then VA, OA and BA intersects at point A. Alright, this is the velocity diagram of OBA. But where is the point D? That point D we draw again. This is the velocity diagram. Again I am explaining what we have drawn. First step, draw vector OB parallel to, what is that parallel to? Vector OB is parallel to, vector OB is the perpendicular to link OB, BO, capital letters BO. Second step, draw a line perpendicular to configuration diagram link AB. Next, draw a line parallel to the configuration diagram motion A. That is parallel to diagram. Next, third step, by measurement, we find that the velocity of A with respect to B, that is VAB, can be measured from this. VA also can be measured. These two things, both magnitude and direction, can be measured. The next, those values are observed as VAB equal to 3.4 meter per second and velocity of A, that is if we measure OA, that is OA length, gives answers 4 meters per second. Now so far we have studied how to calculate velocity of VAB, that is velocity of A with respect to B, and velocity of A measured. Now we want to find out the midpoint. In order to find the velocity of the midpoint D of the connecting rod, we want this velocity, that is what? Angular velocity. That is what meaning. Why we are going to find out all the things? Why we are going to find out? Because it is to be found. It is to be found that what we have to find out? Angular velocity and angular acceleration of point D on the connecting rod. Now divide the vector BA at D in the same ratio of D divides the capital link AB, the space diagram. So what happens? BD by BA equal to, BD by BA is the vector ratio equal to configuration diagram length ratio, capital BD by capital BA. After that, the D is the midpoint of AB. So this D is the midpoint of vector also, midpoint of vector AB. Capital D is the midpoint of configuration diagram's link AB. That same ratio will come as, make it as small d is the configuration diagram of vector AB. Then join O to D, that represents velocity of D with respect to O. That is the velocity of D with respect to O, that is midpoint of D of the connecting rod D. VD is the velocity of midpoint of connecting rod D with respect to O, that is absolute velocity. So how to measure it now? Velocity of D with respect to O, VDO you measure with the help of the scale, that linear distance convert into scale, then the vector OD equal to, then vector D with respect to O equal to 4.1 meter per second. Okay, this is the only up to the portion of velocity diagram. So point is that the next step is how to start. So far we found that we calculated the velocity values. we have to find out the acceleration values. So acceleration of the midpoint of the connecting rod, that ARBO equal to AB, that equal to, what is that? ARBO, that means radial component of acceleration equal to V square by R. What is that? V, velocity of BO square by OB. Substitute over here. That is velocity of BO, that is 4.713 square by 0.15. That is 148.1 meter per second square. Now we know, next step, radial component of link AB. What is radial component of link AB? Radial component of link AB equal to VAB square by AB. What is the VAB? Just now we found from velocity diagram, that is 3.4 whole square by 3.4 square by, what is AB? Length of link AB, that is 0.6, that is 19.3 meter per second square. That is the radial component of acceleration. Now, velocity of VAB equal to vector BA equal to 3.4 meter per second, and velocity of P, velocity of A, that is velocity of A, that means vector OA equal to 4 meter per second. We found these are the radial components. Now, at the point, understand here, very important notice. The notice that very important is that how the radial components and all. Okay. Now very important note. A point at the end of the link which moves with constant angular velocity. A point at the end of the link which moves with constant angular velocity. Then what will happen? Only no tangential acceleration. There has no tangential component of acceleration. And when a point moves along a straight line, very, very important, note 1 and note 2, it has no radial component. What type of component having? It is having only tangential component. The slider A is having tangential component, no radial component of acceleration. Next, at the end of a point at the end of link A which moves with constant angular velocity. What is the constant angular velocity? Formula, that is V square by R comes. But has no tangential. What is the tangential? Formula R alpha. R alpha, that is the tangential component. This alpha means it is constant angular velocity. Then what happens? Alpha becomes 0. Then AT becomes 0. AT, that is tangential component, becomes 0. That's why a link rotates with the constant angular velocity. Which link it is rotating here in this diagram? OB link having constant angular velocity. For that, what is the acceleration of link velocity of B with respect to O? What will happen here? Only radial component is having. Then tangential component equal to 0. Then the total acceleration is only, that is radial component of acceleration. Whereas in the case of slider, radius, the slider, what is the tangential component? Only tangential component. The radial component is 0. Then the total acceleration of the slider is tangential component of acceleration. So that is the discussion of so far. Yeah, let me complete this portion so that how the midpoint can be drawn. It's very simple. How we have drawn that. Now, how to draw the acceleration of the midpoint of the connecting rod. We want acceleration of the midpoint of the connecting rod, that is point D. This diagram we have already drawn velocity diagram. From this velocity diagram, let me read step by step so that we will understand better. Draw a velocity O dash B dash parallel to, draw vector O dash B dash parallel to O dash B dash parallel to BO. This always understand capital letters related to space diagram or configuration diagram. So O dash B dash parallel to O dash B dash parallel to BO. Okay, this focus on acceleration diagram. Don't focus on velocity because we are discussing about acceleration diagram. So parallel to that you draw, that is O dash B dash, that is AB, parallel to that, to represent the radial component of acceleration. That is step 1. that equal to ARBY equal to AB, that equal to 148.1 meter per second square. We have already calculated to some suitable scale. Next point. The next point is that the acceleration of A with respect to B has the two following components. This link AB is having two components. What are that? What are they? Radial component and tangential component. The radial component is in line with the link AB, capital AB. And tangential component is normal to link AB. I am talking link AB means configuration diagram. So you draw the lines parallel to, that is radial component ARAB, we know, known value, you know, and you draw this is the second step. And after that, now perpendicular to that link, third step you draw, that is ATAB. We don't know the magnitude, we know the direction. Now, after that what to do? Yes, read. Therefore, from point B dash, draw vector B dash x. Yes, B dash x, that is the second point. Parallel to AB to represents ARAB. We know 19.3 meter per second square, both magnitude and direction. And from point X, draw a vector XA dash perpendicular to vector B dash. Perpendicular to vector B dash x, whose magnitude is yet to be known. Not yet known. We know only direction. Third. Now from point O dash, which point we know? The motion of the magnitude of the slider we know. So what is the slider component? The total acceleration is tangential acceleration. Tangential component means parallel to the motion of the slider D. Now slider A. Now from O, draw a vector O dash A dash parallel to the path of motion of A, which is along AO. This is third point. Fourth point, draw a line. It will intersect at a point A dash. Then what to do? Next point. What the next point is? Draw A dash to B dash. That is the fifth point, fifth vector. This A dash to B dash is acceleration of, total acceleration of link AB. Acceleration of link AB. Okay. Next point. That is what? Next we want to find out D. Point D we want. That D is the midpoint of AB. A dash B dash. Mark midpoint. Join D to O dash. That is the sixth point. Then if you measure O dash to D dash. O dash to D dash, vector O dash D dash is the acceleration of D with respect to O. In acceleration diagram, O dash D dash is acceleration of D with respect to O. Thus, we will find out the acceleration AD equal to 117 meter per second square. Okay. This is the manner. Next, what do we need? That is the first objective calculated here. The second objective is angular velocity of the connecting rod AB. What is the angular velocity? Omega AB equal to VAB by BA. Substitute known values, that comes under 5.67 radians per second. Next, angular acceleration of the connecting rod. What is the angular acceleration of the connecting rod? That is alpha AB. Alpha AB equal to ATAB by tangential component equal to alpha times radius. This is alpha T. Alpha AB equal to AT by R. That is AB. So that is the angular acceleration of the component that equal to alpha AB equal to ATAB by BA. Why we have used here this tangential component? Why not radial component? The radial component formula is V square by R, V square by AB. Here it comes what? It can also, you can make it. Okay, from that V equal to omega AB, omega. But we want angular acceleration. There is no acceleration component here. That's why we use a tangential component, that is ATAB by BA. From that 171.67 radians per second square. That is in clockwise about point B. Where is that alpha AB? This is alpha AB. This is in clockwise direction. So the tangential component is clockwise direction, ATAB. Alright? That is ARAB. Thus we will find out alpha AB. Okay? It is in clockwise direction. Thus clockwise about point B. Clockwise about point B. Okay? That is the manner we'll find out the accelerations. How to draw the acceleration diagram, how to draw the velocity diagram. Very, very important model it is. Okay, let me summarize what you have studied in this session. We have studied in this session what is rubbing velocity of various links, and when two links are moves in various directions in opposite direction, what is rubbing velocity formula, in the same direction what is rubbing velocity formula, and how to draw the velocity diagram, what is the velocity of the link, how to draw the acceleration diagram of link. And we solved one problem to find out acceleration components of various links by taking example of slider crank mechanism, which included how to draw the velocity diagram and how to draw the acceleration diagram. If you understand thoroughly by number of times watching this session, so you can draw any type of problem in coming any type of problems which were given or which will be occurred during the examination. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.